at systems of equations. And so this first graph gives you a supply and demand line for a company that sells frozen yogurt. So if you're a business major, if you've talked about microeconomics at all or taken that class yet, you may have talked about supply and demand. And so here's an example of that. So question A in the picture, it says, question A says, if the price is $6 per half gallon, what is the supply? So they're asking us to look at the supply line, which would be this line right here. $6 is the price, that's on our x-axis. So if we follow that up to the supply line and look at the point where that corresponds on the y-axis, we get a number of half gallons of 300. So if the price is $6 per half gallon, the supply is going to be 300 half gallons. If the price is $2 per half gallon, what is the demand? So now we're looking at the demand line. So we're going to find $2 and we're going to go up to the demand line, which is going to be up here this time. And that gives us a demand quantity of 300 half gallons. Part C says, at what price does the supply equal the demand? So in business, you'd call this your equilibrium point, and that would be where the two graphs or the two lines intersect. So that would be right here at this ordered pair, 4 and 200. So it says, at what price does the supply equal the demand? They're just asking for price here, and so that would be at a price of $4. And for how many half gallons does the supply equal the demand? And so they're looking for the Y value, the half gallons at that point of equilibrium, which is 200 half gallons. So there's just a little application of these systems of equations that we're going to be working with in this section. So the next part, it says the equations for the supply and demand line respectively are Y equals 50x. So if you remember back to chapter 2, I believe it was, we talked about the equations of lines. The equation for the supply line right here goes through the origin, has a slope of 50. So it would be Y equals 50x. The equation for the demand line, notice it has a negative slope because it's decreasing. That would be the equation Y equals negative 50x plus 400. So this is a system of equations. And when we work with a system of equations, there's three possible scenarios that could occur. So the first scenario is that we have a consistent system with independent equations. And that's what we had in the last example. So when you have a consistent system and it's independent equations, that's the scenario where you get one solution. So that would be one individual unique point where, say, the two lines intersect. There's a little simple example of a consistent independent system right there. Okay? If you have an inconsistent system and you have independent equations, so independent means they're different equations, inconsistent means they don't intersect at all. So in this case, there would be no solution. So what kind of lines, think about this for a second, what kind of lines would never intersect with each other? And they would have to be parallel lines. So this would be the case where you have two lines that run side by side, are parallel, don't intersect. So they're independent because they're different unique lines, and they're inconsistent because they have no solution. They're parallel. The third scenario is that you have a consistent system and they're dependent. So dependent means they're essentially the same equation. And this one's a little bit harder to draw because what you're talking about is the all solution case. So your solution is there's an infinite number of solutions. I'm going to abbreviate, infinite number of solutions. And this would be the case where one line is a multiple of the other. So graphically, they would literally be lying on top of each other. They're the same lines, one's just a multiple of the other. Okay? So let's talk about some techniques we can use to solve these equations. So let's start with this first example. It says to use graphing to solve the system of equations. We're not going to do graphing very often to solve these because I don't think it's a very reliable method, but I did want to throw this in here so we could practice graphing lines since we haven't done that in a while. So the first equation, if you write it in slope-intercept form, subtract 2x from both sides, you'd get y equals negative 2x minus 5. So your slope is negative 2, your y-intercept is negative 5. So let's go to the graph. I'm going to put a point on the y-axis at negative 5. Slope is negative 2. Remember, that's negative 2 over 1. So from there, I'm going to go down 1, 2 units, and I'm going to run to the right 1 unit. And if you have a straight edge there, try to use it. Just do the best you can. This is why I don't love graphing as a method to solve these, because it's hard sometimes to see where they intersect if your graphs are a little bit off. But we'll do the best we can here. Okay, let's do the same thing. Let's graph the second equation. I'm going to rewrite this in slope-intercept form. So first I'm going to add x to both sides. So I have 3y equals positive x plus 6. And then I'm going to divide both sides by 3. And remember the x, when there's nothing in front of it, that's an implied 1. So my equation becomes y equals 1/3 x plus 2. So the y-intercept for this equation is 2. The slope is a positive 1/3, so I'm going to go up 1, and I'm going to run to the right 1, 2, 3 units. Just try to get it, like I said, as straight as you can, and let's see if we can come to some consensus on where it looks like these two lines intersect, because that's going to be our solution to this system. You can see we have an independent, consistent system where they intersect at one point. And it looks to me like that point of intersection is at -3, 1. Okay? We're not going to use graphing, though, very often to solve these. I don't think, like I said, that's a reliable method. Even me, I'm looking at my points just to make sure everything's where it should be, and it looks like it's at -3, 1. A better method to use would be the substitution method. So let's look at the substitution method. So with the substitution method, you want to rearrange one of the equations so that one of the variables is by itself. It does not matter which equation you use, just pick the one that seems easiest. Now, if you'll notice the second equation, that the x is by itself right off the bat. So what we'll do is we'll replace in the first equation, wherever there's an x, we're going to replace it with this 2 minus y expression. So I'm going to rewrite the first equation using substitution. So I'm going to have 5, and then in place of the x, I'm going to put a parentheses, minus 3y minus -6. And so in place of that x, I'm going to replace it with 2 minus y. So I've made that substitution. So that 2 minus y expression replaces the x in the first equation. Then we're going to solve it like a normal equation. The point of this is to get it so we only have one variable to work with. So I'm going to distribute the 5. And then we have like terms we can combine. So let's do that. And then minus 10 from both sides. So I get -8y equals -16. Divide by -8, I get a y value of 2. Okay, we could get fractions for these, but I think most of the ones in the homework are going to be nice numbers. So if you get a fraction or a decimal, I'd be a little suspicious of that. Go back and check your work. Now I'm not quite done. Remember, the solutions to these are an ordered pair, a point on the graph where these lines intersect. So I need to go back and get the x value. You can substitute this y value that you just got into either one of the original equations. It makes no difference. However, I think the second equation will be easiest to work with because the x is already isolated. So let's use the second equation, and let's replace the y with the 2 that we just calculated. Here it is. Well, 2 minus 2, of course, is 0. So my answer is going to be an ordered pair, x comma y. So it's going to be 0, comma 2, and that's going to be the solution to the system of equations. Let's try number 4. Let's use the substitution method to solve this equation. So I don't see off the bat that anything is isolated, any of the variables are isolated, but if you look at the first equation, do you see a variable we can kind of get by itself pretty easily without involving fractions or any crazy algebra? Hopefully you see that I can get the y by itself in that first equation by subtracting the 4x. So I'm going to rewrite the first equation as y equals, you can do 5 minus 4x or -4x plus 5, same thing. And then that substitution, that 5 minus 4x is going to get substituted into the y in the second equation. So let's rewrite the second equation using that substitution. So we get 2x minus 3 and then put in parentheses. Just like when we did function composition back in chapter 2, it's the same idea. Put parentheses and then make your substitution. So 5 minus 4x is going to go inside those parentheses. And now we have an expression where we can solve for a variable. So I'm going to distribute the 3. And then I'm going to add the 2x and the 12x. So I get 14x minus 15 equals 13. Add 15 to the other side. So I get 14x equals 28. And then divide by 14. And we get a solution of x equals 2. Not quite done. I'm only halfway there. I've got to get the other coordinate. So I've solved for x. I need to go back and get the y value. So I'm going to plug that 2 into one of the original equations. It makes no difference which one you use. You can use the version that you rearranged if you want to, or you can use one of these original equations. You should get the same y value either way. I'm going to use the version that I rearranged, this y equals 5 minus 4x. So I'm going to take my x value of 2 and I'm going to substitute that in. So we get 5 minus 4 times 2, which gives me 5 minus 8, which gives me a y value of -3. And then remember, you want to write your final answer as an ordered pair. So our answer is going to be 2, -3. So for these systems of equations problems, there's two main methods to use to solve them all. So one of them is substitution, which we just saw. The other method is called the elimination method. It's also sometimes called the addition method. So if you hear our book or anybody else refer to this, it's also called the addition method. It's the same thing. And the idea with this method is you want to combine the two equations algebraically in some way so that one of the variables will be eliminated or will cancel out. You can add and subtract equations as long as you keep everything balanced and consistent on each side. So look at the way these are lined up. First thing you want to observe is that the x's are nice and lined up, the y's are nice and lined up, and the constants are lined up. That's the ideal way to solve a problem when you're working with the elimination method. And if you notice, if I go ahead and add these two equations together, what will happen to the x terms? So the -2x and the +2x will be eliminated. They will cancel out, and I'm left with 3y plus 2y, which is 5y, equals -10 plus 5, which is -5. And so what that does is it eliminates one of the variables temporarily so that I can solve for the other variable. So I'm going to divide both sides by 5, and I have a solution for the y of -1. Now, just like before, these answers are always involving an ordered pair, so we have to go back and get the corresponding x value. So I'm going to plug -1 in for y into either of the original equations. Makes no difference which one you use. I'm going to use the second one just because it doesn't have a negative sign in it, but you could use the first one. We're going to have 2x plus 2 times -1 equals 5. So then we solve for x. We have 2x minus 2 equals 5. We're going to add 2 to the other side. And we have 2x equals 7. Divide by 2, and we get a solution of x equals 7 over 2. And I said earlier, we're not usually going to have fractions. This one we actually do. I know this is the right answer. So we're going to leave it as 7/2. You could make it 3.5 if you want to, but it's not necessary. It is necessary, however, that you write your answer as an ordered pair. So our x coordinate is going to be 7 over 2, and the y coordinate is -1. Let's look at the next one and see if we can use the elimination method. Now, hopefully you see everything's lined up as we want it. Hopefully you see that nothing cancels out right off the bat. So in other words, if I add the x's together, I'm going to get 5x. If I add the y's together, I'm going to get -4y. That's not going to help me. So what we want to do is select one of the variables, either one, and we want to multiply either one of the equations or both of the equations by something so that when we combine them, the x's will cancel or the y's will cancel. It does not matter which one you use. So let's suppose I want to eliminate the x's. Then one way to do that would be to multiply the top equation by 3, and then at the same time multiply the bottom equation by -2. Now pause for a second and make sure you see why I'm doing that. The top would give you 6x, the bottom would give you -6x. Those would cancel out. I could have used -3 on the top and +2 on the bottom. As long as the signs are opposite after I multiply, they'll cancel out. You could have also eliminated the y's. You could have done this by multiplying the top equation by 7 and the bottom equation by 3. That would have eliminated your y's. There's more than one way to solve these. Do whichever methods you see first when you're working these out. I do need to rewrite both of these equations, so I'm going to rewrite the top equation as 6x plus 9y equals, let's see, 19 times 3, I believe that's 57. Make sure that 3 gets distributed to both sides of the equation. That's essential. If you don't distribute that number to the right side, you're not going to get the right answer. Let's do the same thing with the negative 2. We'll have negative 6x plus 14y equals 12. Okay, so now when I add these together, the x's are going to cancel out, and I have 9y plus 14y, which is going to be 23y, equals 57 plus 10 would be 6, that's 69, I believe. Okay, we're going to divide both sides by 23. Now, had you eliminated the y variables, you would have solved for the x variables first. But because I eliminated the x's, I ended up solving for y first. It does not matter the order you solve them in. So I get a y value of 3. I still need to go back and get x. So I'm going to substitute this 3 into one of the original equations for the y. Let's use the top equation. We'll get 2x plus 3 times 3 equals 19. And then I'm going to multiply the 3's together. So we get 2x plus 9 equals 19. 2x equals 10 when I subtract the 9. Divide by 2, we get an x value of 5. So my ordered pair here is 5, 3. And that's going to be our final answer for this system. And look at example 8. And I think the best method to use for this would be to use the elimination method again. Generally, elimination works best when the variables are all nice and lined up. And if all of the variables, all the x's and the y's have a coefficient, it's going to be difficult to use substitution and solve for one of the variables without involving fractions. So when all the x's, all the y's have coefficients, elimination is probably the easiest way to do this. So let's say we want to eliminate the y's this time. Is it necessary to multiply both equations by something? Well, if you notice that 15 is a multiple of 5, I can go ahead and just multiply the top equation by 3 because that will give me a 15y for the top equation, and I'll have that negative 15y to combine it with in the bottom equation. So let's rewrite this. We get negative 6x plus 15y equals 18. Okay? And then in the denominator, we're going to, or I'm sorry, in the next line, we're going to have 6x minus 15y equals 4. Okay? So I'm going to add these two equations together. Notice something kind of strange happens here. The x's are going to cancel out, and the y's are going to cancel out. So what that means is we've got 0 on the left side equals 18 plus 4, which is 22. Now let's think about that. Does that make any sense? Does 0 equal 22? No, that's a nonsense statement. That doesn't make any sense. So this is going to be your no solution case. So when both of the variables cancel out and you have a number on the other side, some other number that's not equal to 0, that's your no solution case. If you look back to page 1 of the notes, this is the case that we talked about. I think it was the second picture at the bottom of the page. So if you look at page 1 of our guided notes, the no solution case was this. So this is a scenario where we would have two parallel lines if we graph these that never intersect. So they're independent because they're different equations, but they're inconsistent because there's no solution. And so you know that occurs when you have two numbers here that do not match up. Say 0 equals 22. That's your no solution case. Let's try number 9. So we can do the same thing. We can use elimination. We could actually use substitution. This might be a good one to use substitution on because we can solve for y in the first equation pretty easily without involving any fractions. Let's try it just for practice. So take that first equation and get the y by itself by subtracting 2x. We're going to get y equals 6 minus 2x. Now substitute that expression into y in the second equation. So we're going to have negative 8x minus 4 parentheses equals negative 24. In place of the parentheses, we're going to have 6 minus 2x. Let's distribute the 4. So we get negative 8x minus 24 plus 8x equals negative 24. You see where this is going? The 8x's are going to do what? They're going to zero out, and I end up with negative 24 equals negative 24. Okay, is that a true statement? Yes, it is. That's a true statement. So when you're working out these problems, if all your variables cancel, whichever method you use, if all your variables cancel and you get it down to a number equals the same number. So you may get it down to 0 equals 0, or negative 24 equals negative 24, or 10 equals 10, or whatever. But if this is a true statement, that is your infinite solutions case. That's the case where you've really got the same equation. One's just a multiple of the other. It's infinite solutions because every point on the line is a solution. So this indicates that we're going to have infinite solutions. Okay, so that's our consistent dependent situation. Let's do one more. Let's practice setting up an application of these. This is a real simple example, and I think there's a couple in the homework for you to practice with, just setting up a system of equations based on a scenario. So it says, at a concession stand, 7 hot dogs and 2 hamburgers cost $11.50. 2 hot dogs and 7 hamburgers cost $17.75. Find the cost of 1 hot dog and the cost of 1 hamburger. So before we get too into this, let's define our variables. So the cost of 1 hot dog, I'm going to call that X, cost of a hot dog. And then the cost of a hamburger, I'm going to call that Y. So when you have a question like this, start by defining what your X and Y are going to be. So let's set up an equation based on the words they gave us. Remember back in chapter 1, we practiced a little bit with taking words and translating them into an equation. So we've got the first equation says 7 hot dogs and always means addition, right? 7 hot dogs and 2 hamburgers costs $11.50. So my equation that goes with that, 7 hot dogs, would be 7x plus 2 hamburgers would be 2y, costs $11.50. So the total there is $11.50. 2 hot dogs and 7 hamburgers cost $17.75. So 2x plus 7y equals $17.75. Now think about what method you would use to solve this. I think elimination seems the easiest because everything, both the x's and y's, have coefficients. We can eliminate the x's or the y's. Makes no difference. I'm going to go ahead. I'm going to eliminate the x's. So I would multiply the top equation by -2, the bottom equation by 7, or we could do +2 and -7. Does not matter. Let me come down here and rewrite my equations. So I'm going to have -14x minus 4y equals negative, I believe that's $23, -23, $11.50 times 2. The bottom equation, we're going to have 14x plus 49y equals, now I'm going to use my calculator here, 7 times 1775 is 124.25. So now we can add these together. The x's will go away. 49y and -4y is going to give me 45y. 124.25 minus 23 gives me 101.25. And then divide both sides by 45. Now we may get decimals for some of these because we're talking about money, right? So you can have a decimal if you're talking about money, because that would be like change. So we get a y value of $2.25. So the hamburger cost is $2.25. I still need to go back and get the cost of the hot dog, so I'm going to pick one of the original equations to work with. So let's come back over here. Let's say the top equation. We would have 7x plus 2 times your y value, but your y value you just figured out was 225. So 7x plus 2 times 225 equals 1150. Okay, so that's 7x plus 450 equals 1150. Minus the 450, we get 7x, 1150. 7x equals $7, I believe. 450 take away, or 1150 take away 450 would be 7. Divide by 7, and we get a value of x equals 1. Okay, so let's summarize what we've got. So the cost of our hot dog is going to be $1. And the cost of our hamburger is going to be $2.25.